Hello, my name is Karl Littau. I am the CTO here at Intermolecular, and I'll be talking today about some of the work that we've been doing on ALV materials for phase change memory. First, I wanted to thank Dr. Rotzboom and all of the rest of the organizers of the ECS-PRiME and this session for inviting me and giving me the chance to talk a little bit about what we're doing at Intermolecular in this area. So the title of my talk is ALV of phase change and threshold switching materials for next generation non-volatile memory devices. This work is the combination of the hard work of a lot of very bright and talented and hardworking people that I list here. I wanted to highlight a few of them. Valerio Adinolfi and Mario Laudato actually did most of the deposition and electrical characterization work in this session, with the assistance of Ryan Clark and Scott Jewhurst and several of the others. Martin, Son, Vijay, Langshia, they all contributed mightily to either the deposition or characterization or analysis of the materials. And I am the lucky one that gets to share this with you. I thought I would take a little bit of time to talk about Intermolecular. We are not that well known, although we're not a young company by Silicon Valley standards by any. We were founded 16 years ago here in San Jose, California. This was sort of in the heyday of combinatorial materials science and materials chemistry. And the idea being that even with the best planning and fundamental understanding, that the development of new materials for certain applications often did require a lot of experimentation and some phenomenological work. And in that regard, the experimental approach could be to accelerate that work and be able to test tens, hundreds, thousands of different materials and find the ones that were best suited for the application. The founders of Intermolecular came from the semiconductor equipment industry, and using their expertise, they developed a set of 300 millimeter thin film deposition tools in order to take that combinatorial materials approach into the thin film realm for the semiconductor industry. And so we have now over 30 different tools that are useful for depositing a wide range of materials on the same substrate often, and be able to quickly and analyze them for their materials properties and also their application properties, so actually making the devices in question. And since that time, we have specialized in the research and development and materials discovery and pathfinding for many different applications and technologies, primarily in the semiconductor industry. So why would customers work with us? It breaks down into three reasons. The one is by using the combinatorial thin film material science applications and technology that we've developed, we can generate data faster than the traditional approaches. So using high volume manufacturing equipment, we may be able to compared to high volume manufacturing equipment, we may be able to do 10 times or even better in terms of the throughput of experimentation. In addition to that, we not only generate film data, but we also generate data for the actual device operation. So we're actually making devices. If we're developing materials for memory devices, for example, we will make the memory cells and test them for endurance, threshold switching, and speed of write and read, etc. And finally, because many of the materials that we are actually investigating are often very unusual and sometimes are not very fab friendly, often it's to the advantage of our customers to have the early stage pathfinding R&D done in our facility where it doesn't put their current manufacturing, pilot manufacturing, or R&D at risk. So how do we do that? As I mentioned, we developed a suite of single wafer 300 millimeter deposition chambers that are able to deposit a wide range of materials. They're designed for maximum flexibility in terms of operating condition, process condition, and temperature, and be able to deposit different materials even on the same substrate very quickly, often simultaneously. So the picture at the upper left here shows a wafer that has three different regions that have been processed with different, in this case, atomic layer deposition films on the same substrate. And on top of that, we have deposited a number of different top electrodes with different metal films deposited by PVD, site isolated. Each of them could be a different composition and thickness or processing condition. And by generating this stack of materials, then we are then able to fully fabricate devices, for example, in each of these regions and test them for their device properties. So we have a number of different processing systems in addition to our own custom chambers. We have standard chambers that are able to quickly deposit uniform films or etch uniform films or pattern them. We have a suite of physical and optical characterization tools in-house, with the exception of a few like TEM or RBS, which we use partner companies for. We have an extensive suite of an electrical testing measurement. To the point that we can basically test anything that is important to our clients. You know, if they are interested in the threshold voltage drift or speed with which a device will switch, we can test that to the same level that they can. Because we generate so much data, we have a custom suite of informatics tools that we are able to collect, analyze, and process that information, and so that we can develop full mechanism understanding. I won't talk about most of the custom tools, but since this talk will focus primarily on atomic layer deposition, I thought I would highlight the custom tool for that. A 300 millimeter wafer chamber designed and assembled by our engineers here. It is able to deposit different chemistries in 4 different regions on the same substrate. Not only chemistries, but thicknesses, dosing conditions, etc. And we have all the 4 different flavors of ALD that are most common. Thermal ALD, of course, is the most well used. Direct plasma and remote plasma ALD we also have in-house, and we also do have some in situ capability for test and measurement. In this case, highlighting in situ ellipsometry to watch the precursor molecules adsorb and desorb, or watch the film grow in real time. In the 16 years that we've been in business, we've had the opportunity to work on many different material systems. And so this is a highlight of everything that we have touched by either sputtering, chemical, or atomic layer deposition. And as you can see, we've done a lot on the periodic table. Some of the things that we haven't looked at, it's not because we are unable to do it, but mostly because our customers have not been interested in those materials. Other than radioactive materials, you know, we are basically able to touch just about anything on the periodic table, and we have done so either as pure materials or as compounds, often binary compounds, which are very common. Okay, so I'll get into the meat of my talk now, and I'm going to break it down into this set of topics. I'm going to introduce cross-point memory, talk a little bit about that and why it's so significant. And then I will touch on briefly upon our work in atomic layer deposition of phase change materials. The bulk of the talk will focus on our work in OTS, or ovonic threshold switching selectors for cross-point memory, both binary and quaternary systems. And then finally, I'll wrap it up with a conclusion. So cross-point memory. So what is cross-point memory and why is it so significant? Well, let's start with a spectrum of memory technologies used in the semiconductor industry. So this is it's a few years old now, but it's a spectrum of in current memory technologies and emerging technologies put in order of highest performance to lowest performance. And you can see some of them are emerging. ST-MRAM is an emerging technology. FEFET a little bit more behind. Phase change memory, again, emerging. You can purchase them today, and we'll talk about that. But the existing titans of the memory technology, SRAM, DRAM, and NAND, are the ones that we most encounter. And it's interesting. You can see SRAM, very expensive. It's basically a 6-transistor flip-flop. But it's one of the most expensive ones that you can have. DRAM, higher performance than NAND, but more expensive. NAND is interesting. It's a very important technology, very common. We all use it every day now. But it's incredibly low performance. It's very high energy consumption. The raw bit error rate is very high, at 10 to the minus 4 or 10 to the minus 5. Only it takes error correction codes, fairly sophisticated error correction codes, to get the effective bit error rate down to the point that it's actually usable. And its write speed is not great. It is non-volatile, of course, which is a huge advantage, but it's not very good. So why is it so common? Well, it really comes down to the fact that it's good enough, but that it's incredibly inexpensive to manufacture. And that's really where it excels, and that's why it is such an important memory technology. And why is it so inexpensive? Well, in part it's because the cell architecture is fairly simple, but in addition to that, the manufacturing methods have become quite sophisticated, so that now, by going to a true 3D device, tens or even hundreds of cells are manufactured in one column simultaneously by using conformal methods of deposition. The memory cell elements, the floating gates, the charge storage layers are deposited through atomic layer or chemical vapor deposition techniques deep into features, so that all of the memory cells can take very little area on the wafer and be manufactured cost effectively in parallel. And it's really these conformal methods of deposition that have enabled this to happen. So the silicon nitride layers or the polysilicon films are very conformal and can be deposited deep into these features. So the question always is, how can we do better in semiconductor industry? Well, certainly they are low cost, but if we could make a memory architecture or technology higher performance than NAND, more reliable than NAND, but maintain the economies of fabrication at low cost, that would be a potentially disruptive technology that could displace it. The one possibility is cross-point memory. So what is cross-point memory? Cross-point memory, well, simply put, it's the most space-efficient memory technology that exists. It uses a simple grid structure where you have orthogonal bit lines and word lines that every point at which they cross is a memory cell. Obviously, there has to be some kind of material at the cross points that store the information, but assuming that those materials are as small as the bit lines and word lines themselves, then it's an incredibly space-efficient density, and it can be made truly 3D, so that it can be incredibly high density and potentially quite inexpensive. Here's an example of how old it is. This is a picture of a 1/4 of a 1 kilobit core memory cell from, I believe, the late 1960s. So in this magnetic core memory architecture, it used these ferrite cores to store the bits, and they were written by running 1/2 of the write current down the corresponding bit and word lines. So the sum of the current was only exceeding the threshold voltage for switching at the required location, and then the bit switch was detected by the sense line that serpentine wraps through all of the cells. It's very effective technology. Truly has a very good selectivity. Only the interested cell was accessed each time in read and writing. It was a destructive read operation, but that was handled by, of course, rewriting. So anyhow, it's been around a long time, and it's always been attractive for space-efficient memory. Now, modern resistive memory is a little different. It doesn't use the magnetic method for writing or storing the bit, but uses a resistive method. It's a two-terminal device that stores the bit in terms of the resistance level, either a highly conductive state or a highly resistive state. Typical memory materials that are used are things like GST, germanium, antimony, tellurium, that undergo these phase change operations between a crystalline state, highly conductive, and an amorphous state, much more resistive. And that they are accessed by different pulses that will switch the material from the two different states. Now, one of the problems with this kind of architecture is that it is susceptible to so-called sneak path currents. And that is to say, when you have an array, especially a 3D cross-point array, that you are accessing, of course, the cell that you want by running half of the voltage across the corresponding bit and word lines, but then you are also accessing all of the other memory elements in some kind of parallel sneak path. Sometimes it's very tortuous, but it could be relatively short. So that means that the resistance of these cells has to be highly nonlinear. Above the threshold voltage for activation and reading, they have to be on, but much below that, they must look like they are highly resistive so that you're not sensing their state when you're reading, or you're not changing their state when you're writing the cell. And the way that is accomplished is through in-series selector elements. These are very nonlinear elements such that above the threshold voltage, they look like a conductor essentially. But much below the threshold voltage, they are orders of magnitude more resistive. That kills these sneak path currents so that only the cell that you're interested in is the one that you access. Typical OTS materials, typical selector materials, I should say, are OTS materials. These are ovonic threshold switch materials that use an avalanche effect where above a certain voltage and current value, they do switch on and look like a conductor. Below that, they are highly resistive. They are not permanent in that state. Once you drop below the threshold or hold voltage, they go back to their highly resistive state again, and therefore they enhance the selectivity. Selectivities of 1,000, 10,000, or 100,000 or more are achievable in these materials. And this is the selector material that you will find if you were to purchase in cross-section a Optane chip, for example, which is the Intel Micron product that you can buy today that uses phase change memory. So interestingly, if you would take the first product that was shipped that was a phase change memory from Intel and Micron joint venture and measured its bit density, it's interesting. It was actually, even though it is a 3D device, the bit density was actually closer to what you would expect in a 2D device compared to 2D NAND devices. And that's because it is technically 3D, but it is only 2 levels. I think the current products are beyond that, at least 4 levels, but nevertheless, the bit density is significantly lower than the 3D NAND devices that you get in NAND flash. And the reason behind that is the manufacturing method. Unlike 3D NAND, which are made with conformal technologies that can make hundreds of layers simultaneously, essentially, the materials that are used in phase change memory, the selectors and the phase change memory itself, are typically deposited by sputtering. They're multinary materials made of 3, 4, 5 different elements, and in order to maintain the element ratios within them, often sputtering is a convenient approach. But because of that, sputtering is line of sight. It's not particularly conformal, and so these materials are built up one layer at a time with critical lithography steps at every layer. And so they are expensive to manufacture. A 4-layer device is roughly twice the cost of a 2-layer device, so you can imagine making hundreds of layers would be prohibitively expensive, and so it's difficult to reach the kinds of densities that you would want to get the economies of manufacturing that NAND enjoys. So it's a fairly expensive device to manufacture. If we wanted to see the low cost and high performance promise for these phase change materials, we would want to see them manufactured in ways that are similar to 3D NAND. So moving from a layer by layer sputtered approach with critical lithography at every layer to a very approach like 3D NAND, where you have deep features, vias, and trenches that after building up hundreds of layers, you fill them with the active material, the phase change material, and the threshold voltage switching material that's required for their operation. Now, until now, the processes for doing those conformal depositions of these materials for PCM haven't been widely available, and that's the focus of the rest of my talk. I'll touch briefly on what we've done for ALD phase change materials themselves. So GST, germanium, antimony, tellurium, in particular ratios such as here, 2:5, are very common used in phase change memory, both in research and development and in commercially available products. They switch well, they have good on-off ratios, etc. Now, ALD methods or CVD methods for depositing GST have been known for some time, and they are reasonably sophisticated. We were able to combine published reports of this technology using known chemistries, and we're able to reproduce results from literature. Our combination was somewhat unique, and we were able to demonstrate that our reset current density for the ALD films was very competitive with PVD films, and that we could achieve high on-off ratios with very smooth films that were very conformal. So we believe that ALD GST is a very plausible technology for use in the phase change memory themselves. Now, moving on to selectors. Some very smart people within the semiconductor manufacturing industry have told me in conversations that for cross-point memory, especially phase change cross-point memory, the memory cell itself is, while it is challenging, it's really the selector that makes or breaks the technology. It really is the selector performance that can enable the good operation and the product worthiness of phase change memory, a cross-point array. And so that's where the real the rubber hits the road, if you will, and the requirements are more exacting in that space. If you look at the current products that are using ovonic threshold switches, these are usually made up of 3, 4, even 5 different elements. And the interesting thing is that these are not in stoichiometric ratios. Now that's a challenge for methods like chemical vapor deposition or atomic layer deposition. Typically, ALD and CVD rely on the thermodynamics of making stoichiometric mixtures in order to get stable process results so that you can deposit a controlled composition in a manufacturing-worthy method. Now, in the case of non-stoichiometric methods, a different approach will be required. And that is usually to use several different reactions and use nanolaminates in order to target the composition that you want. So you use several binary reactions. The binary reactions themselves tend to form stoichiometric compositions, but then by laminating different materials together in different ratios, you can achieve the composition that you want. Now, we had no experience when we started this program with OTS selector materials or adjusting their compositions in this fashion. And so we thought we would start with a model system, a binary system such as germanium telluride. Germanium telluride is known to be an OTS material and a reasonable selector. It's not the best. It has a high off-state leakage, for example, and its on-off ratio is not particularly good, and reliability is not necessarily that good either. However, as a model system, it was very useful for us to show the ability to use ALD to tune the composition and then compare the selector behavior of our ALD film with what we know to get from PVD. So we were able to do this by combining some known chemistry. We used this chemistry here, the trichlorogermane combined with bis trimethylsilyl tellurium, to form a GETE film with approximately a 1-to-1 ratio. And then by combining it with a new chemistry that we developed, combining tellurium alkoxide, in this case ethoxide, with, again, BTMS tellurium, to form a pure tellurium film. And then by alternating the appropriate nanolaminate structure, we were able to make a tellurium-rich film, approximately GETE4, and then measure its film properties and its switching characteristics. You can see that these depositions with chalcogenide materials are often fairly tricky. Island growth is quite common. Rough films are a challenge. But by modifying the process conditions, including things like discrete feeding, where we use multi-pulses for some of the challenging precursors like the alkyl silyl chalcogenides, we were able to actually get good nucleation and reasonably smooth films, good control of the composition, and also eventually switching, OTS switching behavior, which I will talk about in a moment. We made heavy use of our in situ monitoring capability. It was important for us to be able to watch the adhesion the surface adsorption of the material on the surface, and then also watch the films as they grow. Often we saw selective behavior so that it was difficult to nucleate, long incubation times, and poor quality film. And so the process was greatly accelerated by being able to watch the growth of the films or the non-growth of the films in real time. We were able to make a phase pure material, as you can see here. We have good films with good content of germanium and tellurium, very low chlorine content, almost undetectable in many cases. Carbon content undetectable. The films were smooth enough to see several fringes and X-ray reflectance, and we were able to tune the composition to the ratios that we wanted. We have our own test structures here at Intermolecular. We use a mushroom test structure where we have a small bottom electrode, typically hundreds of microns in dimension, and a very large switching material and a large top electrode. The geometry of the device is defined by the bottom electrode, which is prefabricated, and then on top of that we deposit the different kinds of selector or phase change materials we want to test, and then we put it on our probe station and then test it. Typically, there's a forming operation where during the first switching event, the material undergoes some local rearrangement, atomic level perhaps, rearrangement, and then achieves stable threshold switching behavior after that point. We saw fairly good step coverage with the germanium telluride film. Again, it's a tellurium-rich film of approximately GeTe4. There is some surface roughness on the field and in the feature. This is quite common with chalcogenide materials deposited by sputtering as well. Sometimes it does take somewhat thicker films often in order to get a continuous film and good performance. Typically, we're depositing 20 to 30 nanometers of material. Nevertheless, this is quite comparable to the PVD films, and in the surface roughness and morphology, and it gave good threshold switching performance. More importantly, it also gave very similar switching performance, nearly identical switching performance to what we got for PVD films. So comparing PVD films of the same composition with what we get from atomic layer deposition, we can see that it has the same on-off ratio and the same threshold switching voltage. So this is quite a good result because the deposition method is so different. The source material is very different, of course, sputtering versus ALD. But also the method that we used by using nanolaminates, it wasn't obvious that we were going to see such similar performance. And in the end we did, which was quite encouraging. Quite encouraging for the future of using ALD materials for OTS selectors. So let me switch now to more realistic compositions of selectors that might be useful in actual devices. As I mentioned, GeTe4, it is a selector. The on-off ratio is not particularly good, and its reliability and off-state leakage are not very good either. We know that the addition of selenium to increase the band gap and arsenic will also improve the reliability of the device so that it can see more switching events before failure, and also the off-state leakage and on-off ratios are much improved. This is the chemistry that we used for the individual layers. For germanium selenide, we used a known chemistry that was introduced by Professor Huang's group at Seoul National University, using trichlorogermane and bis-trimethylsilyl selenium in order to form germanium selenide, approximately 1-to-1 ratio. And then we used arsenic trichloride again with BTMS tellurium for the arsenic source. The arsenic trichloride does not react directly with BTMS selenium. That would have been the preferred approach, and I'll talk about that briefly in a few slides. But we needed the more reactive tellurium alkyl silyl in order to get the arsenic into the film. As you can see, we were getting, again, phase pure material. We saw little evidence of any halogen or carbon in the film, and we were able to achieve reasonable ratios of the different elements. I should stop here just to point out that, again, Intermolecular, we are a a contract research and development organization where we do materials development and screening for our clients. This particular work was an internal activity, and that's why one of the reasons that I can talk about the work so freely, and because it's not proprietary to one of our clients. But we did not undertake this activity in order to determine the best composition for a quaternary OTS selector. We were doing this in order to demonstrate our capability in this space in order to do this kind of work for our clients. And because of that, we did not extensively explore this particular elemental space, this quaternary space, or other multinary spaces in order to optimize the ovonic threshold switching performance of the material. And so this material, while it does have reasonable performance, as you will see, it is not optimized. It certainly could have better performance in terms of perhaps reliability or off-state leakage, although it is greatly improved over germanium telluride. So I just wanted to point out that, again, we did not explore this phase space significantly. In fact, we were quite fortunate that the first compositions that we looked at performed so well, and I will show that to you in a moment. One of the great things that we were able to discover for this is that this particular chemistry gave actually quite smooth films. So films of 20 nanometers in thickness actually had peak to valley distances of only 2 nanometers. So quite smooth for a chalcogenide-based material by any method of manufacturing. So that's quite encouraging. Interestingly, the inclusion of the arsenic was problematic. We did find a chemistry that worked, the arsenic telluride, to bring in arsenic into the film, which is quite important for reliability. But it was interesting that the arsenic telluride did not deposit on our electrode material nor on dielectric materials. And so that was a challenge. We could not actually get this chemistry to work if we just tried to grow it as a monolithic material on our electrode. We actually had to use a nucleation layer, in this case of germanium selenide. And the reason behind that, if I can go back to our chemistry slide, we feel that it is because the arsenic trichloride is insufficiently reactive with the other chemistries or the surface. It doesn't irreversibly chemisorb on the surface. It probably doesn't physisorb well enough in order to drive this reaction forward sufficiently. So what we found is by putting down a germanium selenide layer first, that was reactive enough for the arsenic trichloride to stick to. Presumably, the chlorine likes to bond to the germanium and selenium in the film, and so it would partially react the ASCl3, and that would give a good nucleation for the film to grow. And after that point, then we could grow a thick film of the second layer. 2 nanometers was sufficient. It is a heterostructure. However, our estimate of the band gaps and electron affinities is such that we feel there's very little band offset between the 2 layers. So the advantage of this is really in terms of just the process capability and being able to get the film to grow the composition we wanted. The films were excellent ALD films. They were able to coat these 20:1 aspect ratio test structures quite well. They are very conformal, so it's a well-behaved ALD process. You can see in the EDS line scans done at the top, middle, and bottom of the film that the compositions are quite uniform across the depth of the feature, and you can see the evidence of the germanium selenide nucleation layer that we used. But after that nucleation layer, the compositions of the films are actually quite stable across their thicknesses and throughout the depth of the feature. Again, we used our own test structures, a mushroom vehicle, in order to look at the switching behavior of the devices. Again, after a forming pulse, the threshold voltages were quite stable, and the subthreshold currents were quite reproducible. And the on-off ratio of the devices was several orders of magnitude, which was quite excellent. Using them in pulsed operation, we were able to show switching times of 100 nanoseconds and good repeatable performance. And then, of course, with longer pulses, we were able to measure the subthreshold voltages, and they, again, quite stable and with quite good on-off ratios. The most surprising thing was the endurance of these devices. Again, essentially right out of the box, first compositions that we were looking at, we saw reliability in excess of 1 billion cycles. So they almost made 10 billion cycles before failure. So they were quite good. And you can see that the subthreshold performance is quite good. Threshold voltage is quite stable across the billion cycles, and the selectivity between half a volt and 4 volts operation in many orders of magnitude. So these are quite good performing OTS materials. Again, the subthreshold current was quite stable across these, and the threshold voltage was also quite stable beyond 1 billion cycles. So an ideal selector also is one that has no memory. That is to say, its threshold voltage and its on-off ratio, its performance is always the same, regardless of how often or how recently it's been activated. That turns out to be not the case in OTS materials. They do have some memory. They tend to remember their switching performance. So if one that hasn't been switched for many seconds or minutes will behave slightly differently than one that was just switched 100 or 200 nanoseconds prior. This is typically called a threshold voltage drift, and it obeys a log normal distribution of relaxation times, so that you see a logarithmic dependence measured typically in millivolts per decade of threshold voltage drift. We measured that for this composition, and it gave 50 millivolts per decade, which is actually quite reasonable. It can be better. We know that the addition of other elements into this mixture can actually improve the threshold voltage drift. But as a starting point, it's quite reasonable. There are many materials that are much more susceptible to threshold voltage drift than this. And we feel that there's plenty of room for optimization and inclusion of other elements to further improve the performance of this device. So let me wrap up and give you some conclusions. So I hope I have convinced you that 3D non-volatile memory architectures, especially cross-point memories, do require series-connected nonlinear selector elements to make them viable. And that the choice of these selector materials requires simultaneously meeting several different metrics, including the performance, so its individual performance, how it switches, its reliability, its cost, and the ease with which it's integrated into the device. And I hope that I have shown that a stable, low-temperature ALD process for depositing chalcogenide alloys with great morphology and conformality. Now, I didn't mention the deposition temperature. Typically, we were depositing these below 100 degrees C, so it's quite low temperature. Nevertheless, they gave very good performance in the films and in the devices that we measured. I touched on GST, that we have been able to show ALD of GST with good switching performance. And I have demonstrated and shown to you the results from one of the first integrations of ALD arsenic in OTS selector materials, and that it really does have outstanding performance, especially for a new material, without optimization for the composition. So I wanted to thank you again for giving me the chance to talk about some of our work in ALD phase change materials, selectors, and memory. And I'll look forward to answering some of your online questions later. And again, thanks for listening.